In this lesson, we will be talking about the area of certain regions and how to find those areas using summations. Just to give you an idea of what problems lie ahead, on the left side here, I've got a coordinate plane set up and I've got a function down here, y equals x plus 2, but we only want to look at this function, the graph of this function, on the interval from 2 to 6. So that will look something like this. From 2, 4 all the way over to 6, 8. And what this idea of area is trying to get at is we're trying to compute the area only on this interval from 2 to 6 between the function and the x-axis. So this is the area we are trying to compute right here. And in this current form, it's relatively easy to compute. We can divide this area into two different sections and see that you have a triangle with a base of 4 and a height of 4, and that you also have a rectangle with a base of 4 and a height of 4 as well. And so you can figure out that the total area for this region is 8 for the triangle and 16 for the rectangle, which gives you 24 units squared for that area. And that's easy because we have formulas for this, computing the area of a triangle and computing the area of a rectangle, no problem. The problem lies when you start trying to figure out the area of a quadratic expression, say. So the graph of this thing, if you graph this function only between -1 and 3, will look something like this. It goes, there's a point at -1, 8. There's a point at 0, 9. There's another point at 1, 8. There's a point at 2, 5. And then the last point over here is at 3, 0. So this function looks something like this. And since we're interested only on the interval -1 to 3, we are trying to find an area that is here. And this becomes much more difficult because we do not have a standard formula to help us find the area of things that are rounded. I mean, we could find the area of a circle, but this is clearly not a circle. So the point of this section is to figure out how we can find the area of something like this. In order to help find the area for curved regions, we will first need to study the idea of summations. First, some notation. The summation notation looks something like this. And going through and dispelling what each part means, here in purple, this is a capital sigma. And the capital sigma, whenever you see that, that's telling you to sum up all the terms. The next thing I want to point out to you over here in red is this a sub I. I call this the argument. You may call it the expression being summed, the argument. I refer to it as the argument. Down here, the I, that is the index of summation. And the index of summation essentially tells you what variable will be used in the argument. And then these last two bits of information here, let's see, in green, this and this are what we call bounds. the bounds of summation. So here we have the lower bound of summation, and up here we have the upper bound. And one thing about the bounds that I would like to mention is that the lower bound usually starts at 1, and the upper bound will either be a number or n. So we can either have a number here or it'll be n. Either way, it is some sort of constant that's being that is written up here. So we have to consider n being a constant. N is a constant. So with this, it's time to explain what happens in a summation. So I'm going to rewrite what's up there. So summation as I goes from 1 to n of a sub I. How a summation works is that the variable is I, and this is what changes. So you hear me say the summation as I goes from 1 to n of a sub I. So what this means is that I will start at 1. So that means I'm going to substitute a 1 in for any I that I see over here. So I know my first term will be a sub 1. So what comes next is that this summation tells you we're going to move I, as I said, the summation is as I goes from 1 to n. So we're traveling from 1 to another number. And we do that by adding 1 to I. So we start I at 1. If you add 1 to that, the next one is 2. So we know that we're going to have a term a sub 2. We're going to have a term a sub 3. And dot, dot, dot. We're going to go all the way out to a sub n. And you know that you're going to stop at a sub n because your upper bound is n. And the very last thing here is the summation. This tells us to add up all of our terms. So we're just going to come over here and put plus signs in between all of our terms. And the plus signs, the addition, will also surround the 3 dots. These 3 dots represent every other term that's in here that we do not want to write out. On this page, I just want to go through a couple examples very quickly on what expanded sums look like, so you can get a feel as to what's happening with this these numbers as you expand out a sum. So in this first sum, we have the sum as I goes from 1 to 10 of I. So just very quickly, the very first thing we're going to do is we're going to take 1 and substitute it in for I on the other side of the equation here, so 1. Then as you know, we need to increase this value of I by 1. So 1, and then the next value is 2. Oops. 2, 3, 4, 5, 6. You might be wondering, when do we stop? We stop at this value up here, 10. So we have 7, 8, 9, and 10. And since this is a summation, we have the sigma here. We need to add all of these values up. Now you can go through and figure out what this is all added up. I believe the answer is 55. But I just want to really concentrate on showing you what it looks like to expand a sum. So in this next example, there should be parentheses here. What this means is that the first term, we will take 1 and substitute it in for I. So the first term is going to look something like this. 2 times 1 plus 3. And to that we're going to add, if we increase I by 1, we'll have 2 times 2 plus 3. And trying to do this for 42 terms would take a very, very long time. So what we can do to shorten this is we can say plus 2 times 3 plus 3. And in order to shorten this, we can add ... with another addition sign. And then we can go right to the very last term, which is 42. If I stops at 42, then we can write 2 times 42 plus 3. So all of this ... took care of every other term that we didn't want to write. It would take a long time and a lot of space, so we can write a ... This very last one, this last summation down here, we can write out similar to this one, but instead of stopping at a number like 42, we will be stopping at n. So we can write this as 1 plus 2 squared plus 2 plus 2 squared plus 3 plus 2 squared plus ... all the way over to n plus 2 squared. One thing I want to point out to you is that if you decide to use notation like this, that you write out the first 3 terms, and then you can do your plus ... plus your last term. Alright, on this page, we want to actually go through and evaluate the sums. That means substitute the numbers in where you can and give a numeric answer. So in this first example, I want to see something like this. Let's see, this is 1 plus 1 squared. All right, that's what happens when you start I at 1. We substitute the 1 in, there it is. The next one is 1 plus 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus, and finally the last term, 1 plus 5 squared. So this first term becomes 1 plus 1 is 2 plus 5 plus 10 plus 17 plus 26. And when you add all of these numbers together, you get 60. Alright, so there's the answer for that first summation. Looking at this second summation, if you repeat the same process, you'll get something like this. All of these 11 numbers cubed add up to 4,356. Alright, looking at this last one, I'm not even sure if I want to do this. There has to be an easier way. Well, let's write out the first 3 terms and see what happens. This ends up being 2 times 1 plus 1 times 1 minus 4. Plus, that is the term for when I equals 1. Now we've got to make I equal to 2. That's 2 times 2 plus 1 times 2 minus 4. Plus, the third term, 2 times 3 plus 1 times 3 minus 4. Plus, plus, so we can write this shorter, which is nice. 2 times 59 plus 1 times 59 minus 4. Okay, well, we were able to expand it out, but all of these other terms covered by this ... we don't know what they are. And then once you go through and figure out each term individually, you have to go through and then make sure you add them up correctly. There's got to be an easier way. Here is the easier way. We have these formulas for certain sums that are much easier to compute. In this first one, if you're summing up I from 1 to n. So if you're adding up the numbers 1 plus 2 plus 3 plus 4 plus dot 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 all the way up to n, you'll get this. N times n plus 1 all over 2. And we have similar formulas for when you're adding up a bunch of terms that are squared. So 1 squared plus 2 squared plus 3 squared all add up to this. And there's a similar formula for when you're summing up the cube of integers, positive integers. And finally, this one is probably the most revolutionary way to write multiplication ever. There is no no variable in this summation. So a very quick example of this is if you are adding, let's see, your index of summation ranges from 1 to 15, and you just have a constant here, 9. That means you're adding 9 plus 9 plus 9 plus dot 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 plus 9. You're doing this 15 times. You're adding 15 9s together, and that is simply multiplication. 15 times 9 is 135. So one other quick example just to show you what happens, that this n in the upper bound is the same n as you have in the other side of your equation, your formula. If you look at this example here, if you want to sum up all of the cubed numbers, I goes from 1 to 35, which without the formula would take quite a while to figure out. We know that the formula up here states that whatever this upper bound is, you're going to square it. You're going to add 1 to the upper bound and square that, and then divide it all by 4. So that gives you something that looks like this. So now we have a way to quickly sum up many consecutive digits, or the squares of many consecutive digits, or the cubes of many consecutive digits, as well as summing up a constant many, many times. In addition to this, there will be some properties that you need to know on the next page. When you look at summations, generally speaking, there won't just be one term as in the previous two examples. There could be more than one term that have the index of summation in it. And so if you have a sum or a difference of two terms with I, then we can separate the terms accordingly and give each term their own sum, and then add or subtract accordingly as to what sign is between those two terms. The other property that you will need to understand is that if C is a constant, this constant, then the constant can be taken out of a summation. You can see here this C is included in the summation, but in this side of the equal sign, the C is now outside of the summation. On this page, you'll see a couple examples using the sum and difference rule and the constant multiple rule from the previous page. If we wanted to expand this sum out, the sum as I goes from 1 to 5 of 4i, it would look something like this. So now, to make this easier, instead of multiplying 4 times 1 and 4 times 2 and 4 times 3 and 4 and 5, I want to common factor the 4 out to look something like this. So the 4 has been common factored out of each term up here. And then if we rewrite this sum using summation, this will look something like this. So you can see that when you have a constant inside of a sum being multiplied to an index of summation, you can just common factor it out to the front. Now if you go through and actually figure out what this summation is, it ends up being 4 times 15, which is 60. So you can go through and figure out what that summation is on your own, see if you can get 60. To example 2. In this second example, you'll notice that we have the sum as I goes from 1 to 16 of I plus 3 times 4I minus 1. As this problem stands, we cannot just use the formula for I here and for I here to figure out what the sum will be from 1 to 16. We must first FOIL this out. So if you see any multiplication, do that first. So this is going to be 4I squared plus 11I minus 3. So now what the separation of this looks like using the sum and difference terms, or sum and difference rule, is it's going to expand out to something like this. We can take the sum of each term individually and just keep these signs consistent when we write them out over here on the right. So we have the sum as I goes from 1 to 16 of 4I squared plus, that's this plus sign right here, the sum as I goes from 1 to 16 of 11I minus, that comes from right there, the sum as I goes from 1 to 16 of negative 3. Oops, I mean of positive 3. There we go. So there's the sum and difference rule being applied. You can now common factor out the 4 in this first term with I squared and the 11 in the second term with I, and this just becomes the constant times 16. So that last term just becomes minus 48. So if we rewrite it, it'll look something like this. And the next step will be to apply the formulas for I squared and I, and for 3, using 16 for our n in every one, and that'll give you something that looks like this. Remember, the sum for an I squared is your upper bound times your upper bound plus 1 times 2 times your upper bound plus 1. So 2 times 16 plus 1 is 33, all over 6. The formula for the sum of I from 1 to 16 would be the upper bound times the upper bound plus 1, which is 17, all over 2. And when you're summing a constant, you just multiply the upper bound times the constant to get 48. And over here on the left, when you compute or evaluate all of these numbers, you will get 7,432 for your final answer.